Thank you so much for inviting me. It's my privilege to speak in front of so many very esteemed doctors. So we will discuss. I will discuss two of our techniques we have proposed for ECG signal classification and nuclei segmentation. So first technique, which we named as CLI-NET, is an AI model for ECG signal classification. So ECG is a very simple but very vital diagnostic test for many cardiovascular diseases. And because if we can do non-invasive tests in a low-cost manner, we can detect some of the issues very early and save many people's life. And nowadays, many of the wearable devices, such as for example Apple's smartwatch and so on, so they already have heart monitoring capability. So if we can get those signals, and those devices themselves can have an AI engine or AI algorithm to process that ECG data, then we can have diagnosis also, right? And so he can be alerted in case of any life-threatening disease, or he can rush to the nearest doctor. So that's why these wearable devices, they are very ideal for running AI-based lightweight classification techniques. So that is our overall use case. So our idea is that we have ECG signal which is obtained either from ECG machine or from a wearable which takes ECG recording. We feed it to the AI model, and then we can find out the rhythm class. And based on this, we can do the ECG diagnosis. And if this AI model can run right in this smartwatch, that is really a Sone pe suhag kind of thing. So this is our overall AI model. I will explain its components, but overall it has 4 blocks. One is the convolution block. I'm sure you must have heard of the name convolution. Another is LSTM, long short-term memory. Then there is involution, and finally we have fully connected layers. So this fully connected layer simply convert this data in one of the classes. So I will so for example, these are the classes in the IC-CAT data set. These are the 8 classes, and here are their illustrations. So this is for example VFB, VFT, SVT, VPD, and so on. So you can see probably for a human it may not be so easy to detect, especially for example these 3 are quite similar to my eyes, and some of them are life-threatening, some of them are not life-threatening. So we have to differentiate between them. We should be able to identify this life-threatening rhythm classes as early as possible. So now let us discuss our proposed model. So these are the 2 components which were already there in the previous network. So just to mention them. So convolution is a probably very basic operation in any neural network which captures location invariant features. So by location invariant means, for example, suppose if we have a picture of a bird and we want to detect whether it has a beak. So whether the picture is whether the bird is at the top of the image, any part of the image, we should still be able to identify the beak. That means it does not matter where in the picture that beak is, but the features of the beak are more important. Its location is not so important. So that is the meaning of location invariant. That is, so convolution is bread and butter operation for all neural network algorithms. Second part of our model is LSTM. So convolution does not take time into account, whereas LSTM also takes temporal. So temporal means time-based dependency. So how does the signal changes over time? That is what LSTM detects. LSTM is a sequential model. Nowadays, there is also transformer model. So all this GPT and all, they are based on transformers. We have all heard of ChatGPT and so on. They are all based on transformer, but they may be slightly more complex for a wearable device. So that's why we have used this LSTM, and it's also very simple. Then a novelty which we bring is use of involution. So involution is somewhat more recently proposed, operator, which is like a complementary operation to convolution. So it is used for capturing long-range spatial information. So I will highlight what is its use. So it helps us capture subtle differences among various classes of arrhythmia. So as I said here, like these are 3 classes which are very difficult to distinguish for human eye and even for ML algorithm. If you see this AFB, it has irregular long range patterns. Some of, like here, the distance between these 2 are not same as the distance between these 2. So we need to be able to see the long range pattern, only then we can distinguish. So if we use involution, It helps us differentiate between such kind of irregularities. And now involution has spatial agnostic property, which I will discuss on the next slide. So this helps us capture the long range pattern. So convolution and involution, they are complementary operations. Convolution is spatial agnostic. For example, if we have a filter, or it's also called a kernel, the same kernel we will use across the image. For example, if I'm trying to detect a beak in a bird's image, then wherever the beak is, I will be able to identify because I'm revolving or rotating my kernel on the entire image. But convolution is channel specific. That means in different channels, for example, in any image, we have 3 channels: red, green, and blue. Okay, so our approach to we use different filters to extract different properties in different channels, because how we operate on a red channel may be different than how we operate on a green or blue channel, because actually every color encodes a specific information. For example, for detecting a grass, the green color is most important. Now coming to involution, involution is channel agnostic. That means the same filter is used across all the channels, whether it is red, green, or blue, but it is spatial specific. So that means here the filter that is used for different spatial locations, they are all different. They are not same. Whereas in convolution, the same filter goes in the entire image, but in involution, for every spatial location, we have a different filters. So now we can see these are complementary operations, and that is why we have used them to bring their best together. And although I'm not shown here, but in our paper we have shown that if you remove convolution, then also it is not good. If you remove involution, then also the performance degrades. Now, coming out to our further novelties. So the conventional neural networks, which previous researchers have proposed, they use small kernels like 3x3. So 3x3 will be, that means it has 3 rows and 3 columns. Or 5x5 means it has 5 rows and 5 columns. So with small kernels, we have small number of computations so that our network is lightweight. Wherever our program is running, or our algorithm is running, we want energy consumption to be small. Otherwise, nobody will be able to use it in the real time. If you have a portable device which takes a lot of energy, then the battery will be drained very soon. People will just throw it away. But we have found out that if you use large kernel sizes, such as, here when I say 31, it means 31 cross 31. Here, so here we have used large kernel size 31, 36, 41, not small kernel size like 3 or 5. So this has provided us better accuracy because it is able to capture high receptive field so that we can capture long range information. For example, with 3x3, I can only look at 3 subsequent pixels. With 5x5, I can only look at 5 subsequent pixels or the data samples. But with 31 cross 31, right? That this is 1D, so that means 31. So I can look at a very large, time instance and be able to find out in what way our signal changes over 31 time steps or over 41 time steps. So as you can see, this will definitely give us better information. Then another novelty is that previous works just use, for example, only one kernel size fixed, either it is 3 or 5 or 31, just one fixed size kernel. But if we only use a one fixed large kernel size, we cannot extract subtle variations in the ECG signals, because for some of the classes, the variation happens over a small, period of time, but for other signals, it happens over a large period of time. So to be able to capture both long range information and short range irregularities, we use multiple size kernels, not just 31 or not just 41, but 31 and 36 and 41. Right. So in this way, you can see that we have brought certain key ideas, together to be able to extract better performance. So now coming out to the results, let us see what are the numbers. Is it like something good enough so that we can trust it, or is it just maybe academic exercise? So these are the metrics we have used. One is precision. So TP means true positive. That means if my says it is, yes, positive, and the ground truth is also positive, that is true positive, right? And similarly, we can say false positive means, and similarly false negative and true negative. True negative means my algorithm says it is negative, and ground truth also says is negative. So based on this different combinations, the researchers use different metrics. For example, recall is very important metric here, because if recall is poor, it means I say that your class is VFB, but your actual class is probably SVT, which is really bad, because you may have some life-threatening symptoms, but I say no, don't worry. That means recall is very important metric. And so here are our first results from the ICCAT dataset for these 8 classes. This is the class-wise accuracy. That means how good we are in being able to detect the signal of a certain class. So as you can see, like VFB and VFT, these are life-threatening. So these are life-threatening. So we will definitely place the highest focus on being able to detect these classes, and others are also important. So there also we have very good accuracy, very good recall accuracy and precision. Overall, if we summarize across all the classes, then we have close to 99.77% recall and so on. So it is very close to 100. That means in some cases we do mispredict. Now only a doctor can find out whether that is severe, whether it is trustworthy, whether we can trust it, and so on. There is another data set from MIT. It has 2 lead ECG signals from 48 patients. Here there are 5 rhythm classes. Now there is, at least from a non-medical perspective, we don't know whether, I think this data set is completely different from that data set. So here, this is the class-wise results for each class. Here also we have obtained more than 99% recall and accuracy, close to 100% precision and specificity. And we have also compared our work with the previous works. So for example, because these works have also been done on the same data set. So for accuracy and precision, the bold means the best. So here our model is the best. And in recall, we are probably third number, right? Or third or fourth number. But on all other metrics, our results are the best. Now coming to the next, technique that we have proposed. So this is for segmentation. The previous work was on classification. Let me show you a difference between classification and segmentation. In classification, we assume that whatever is your input data or your image, it has only one object or one signal. So classification means to find out whether it is cat or dog or Elmira or a motorcycle. In localization, we also find out in that image where is that object that we have found. In the object detection, we create a bounding box. In object detection means there can be more than one object. So for each object, we have to detect and create maybe a rectangular bounding box which completely surrounds that object. But this is not very tight bounding box. In instance segmentation, we create a very tight mask around that object. So here you can see that is what is segmentation. So when I say this right now, I'm talking about nuclei segmentation. So here, because we know that nuclei, the cells are very small in size. So here object detection has no point. We have to do segmentation. So segmentation is more challenging than classification. Classification is very simple because there is only one object. So here our goal is to do nuclei segmentation from HE stained whole slide images. This nuclei segmentation is very vital for the histopathological diagnosis, for treating several diseases or diagnosing several diseases. But in real world, we know that there are noise-infused intensity variations and uneven staining. So a different part of the image may not be stained uniformly. So we need specific, techniques to be able to, get good performance. This is our overall architecture. This overall architecture has 2 broad, components. One is called encoder, and another is called decoder. So first we, take an image, encode it into a latent space, and then we again, decode the image and bring it to the same dimension as the original dimension. And that helps us to, superimpose some kind of mask that, okay, this pixel belongs to this cell, this pixel belongs to this cell. So to briefly explain the components, so in classification, we generally use a pooling layer. So this is the pooling operation. For example, this is the max pooling operation. For example, max pooling with 2 × 2 means in this 2 × 2, what is the maximum value? That is 37. in this 2 cross 2, what is the maximum value? That is 112, because it is usually the highest value that actually creates the what you call creates an excited response. That's why max pooling only takes that, and it helps us in reducing the number of computations. But for segmentation, this pooling layer is very harmful, because here you can see we have lost the original spatial dimension. From 4 cross 4, now we have come to just a 2 cross 2. Our data has become from 4 cross 4, it has become 2 cross 2 size. So that is not good. So in classification it is okay, because in classification we just have to find out whether the image has cat or dog or not. But for segmentation, this is very hard. So what we do, we propose a feature enhancement block which compensates this information loss, okay, and generates high resolution feature map. We should not use the resolution, because in segmentation is all about resolution. So it concatenates the downsampled version of the original image to preserve the pixel intensities. Then here also we use LSTM in the encoder decoder path. So I explained this, the whole thing was encoder decoder, and in between we have this LSTM, which acts as a feature mixer block, where the low level features are mixed and passed to the decoder for mask creation. Our ultimate goal is to create a mask. I will show you some sample mask. And to reduce the model size, we use depth-wise separable convolution. So there is a standard convolution which has huge number of parameters, but in depth-wise separable convolution, the number of parameters are much less, because we operate on each channel separately. So here this is used in this depth-wise separable convolution. So I will show you the effect of this when I show the model size. See, because if I want to run a model, maybe in a smartwatch or in a portable device, it should be very, very lightweight. If it takes a lot of memory, then not only the price will increase, but the memory requirement will also increase. So this is because this segmentation task, here the metrics are different. So here the metrics are dice, score, AGI. PQ is the panoptic quality, which is composed of segmentation quality and detection quality. And this is the segmentation quality, their formula. So here G refers to ground truth. So, and P refers to prediction. So if my prediction exactly matches the ground truth, then it is really good segmentation. So we have shown the results on 3 data sets. One is concept, another is Kumar data set, another is CPM 17. It has this many nuclei. Total number of these images are this much, and size of the images 1000 cross 1000, and number of cancer types. Here it is just one. Here there are different number of cancer types. So on Kumar and CPM 17, we only do binary segmentation, because that is what the data set provides. So here, this is the original image, and this is the ground truth, and this is our prediction. If this prediction is same as ground truth, so this is the ground truth mask, this is the predicted mask. If our predicted mask is very close to the ground truth mask, then we are good. Otherwise, our prediction is not correct or not accurate. And here in this concept data set, there are multiple cell types, nuclei cells available. So that's why here we can do multi-class segmentation. We don't just do segmentation, but also classify to which class each cell belongs to. So here, these are all healthy, and you can see like here, this one is different from here. So there is some misprediction, but still we say that the results is reasonable. Now let us see the numbers. So here the number of parameters are, this is our FeedNet model. 2 variants we have designed by generating some, this is without depth-wise separable convolution. So if we use depth-wise separable convolution, the number of parameters that reduces from 26 million, it becomes only 16 million. So 16 million, to give you an idea, if 16 million is the number of parameter, that means 64 megabyte is the size of our model. 64 megabyte. It is slightly the larger end, but we can probably further bring it down. And this is our metric, MPQ. So the best results are obtained by this, and ours is second best, just a little bit behind than this technique. But the point is, this network is very, very bulky. So maybe 10 times more bulky. So maybe doctors may not prefer using it because it is very bulky. And these are the detailed results. This is my just last slide. So here on concept data set, maybe HoverNet is generally the best. Our technique is best on some metric, not on all the metrics. We are generally either the best or second best. But on Kumar and CPM, we are, better. So here on most metrics, actually this PQ metric is the most important metric. So here we are best on PQ metric. Here also we are second best, and here also we are best on the PQ metric. So different metrics are conveying different amount of information. So to summarize, thinking in terms of future work, especially for this, very esteemed audience, currently we are using data sets which are created by Western people, people also have to use one Mexican data set. Of course, there are many Indian data sets also available, but if we can do these studies on real world data sets, doctors and all of us come together to solve real world challenges. We can use some Indian specific data set by addressing privacy concerns and so on. So that will really help and convert some of our academic studies into real world studies. And then as a next step, maybe some engineers, they can help us, making these techniques very lightweight and, solving all those manufacturing and design challenges and democratize access to them so that more people can use. So with this, I, stop my presentation. Thank you so much.